Welcome to the Legion Strength and Conditioning Podcast. You can check us out at legionsc.com or follow us on Instagram at legion.sc. All right, we're back for Science with Sergio number 2, again to talk about lactate and clear up some horrible misconceptions and prejudices that are being, forced upon this innocent molecule by the oppressive culture of fitness. So we're going to try to talk about another George Brooks paper. Last time we talked about a collaboration between Inigo San Milan and George Brooks. This time it's a review paper from George Brooks, who's one of the major figures studying lactate. And this one is called The Science and Translation of Lactate Shuttle Theory. And I don't know if is lactate shuttle theory, is that George Brooks's his pet project, so to speak?
Yeah, so I think that was termed in a study about 30 years ago, but it wasn't really considered to have any other broader application until he started looking into it. And he was like, oh, there might actually be something here.
Awesome. Well, yeah, this is a pretty dense review paper, and I was saying to Sergio before we actually started recording, the paper's like 20 pages, and I was like, okay, this will take me about an hour to read probably, and I read for half an hour and I was like, oh man, I've really read 6 pages of this. I got to pick up the pace. And then I tried to read faster and, click on fewer references and just kind of move through it. And in the second half hour, I read 7 pages. So, 13 pages an hour is a pretty slow clip for reading, but there's a lot of really interesting and dense information here. It kind of summarizes, across the board, all of the different pieces of the lactate shuttle theory, just ways that lactate is transported around the body, common misconceptions about lactate, different uses for lactate in different tissue, some relationships of lactate to various disease processes. So just like a real grab bag of information. And, for our purposes, I think that we're kind of trying to tread the line between going into the weeds of the science and making some of that stuff interesting to folks in the sort of like CrossFit functional fitness space and actually providing some practical recommendations. So we don't want this to all be practical, but we don't necessarily want to dig too deep into lactate's role in angiogenesis or whatever, which may or may not actually be relevant. So for today's purposes, we spoke last time about some misconceptions about lactate and just the kind of general belief that, oh, my legs are locking up on the assault bike. It's the lactic acid. My lats are sore from doing a bunch of pull-ups. It's the lactic acid. And this just sort of general, disparagement of lactic acid and blame of lactic acid for all kinds of negative exercise outcomes. And the reality is that that lactate, which is different than lactic acid, is a very complex molecule that's actually probably positive in a lot of ways for actual exercise performance. And so we wanted to kind of dig into some of the pieces of this paper and explain the lactate's actual role in the body and how it potentially does relate to fatigue. So, Sergio, if you were to sort of start off and say, okay, just like a general explanation of lactate's role in fatigue, what would you say?
Sure. So, and I think you alluded to this a little bit, but I know I've heard the idea like a million times that while you're exercising, it's that like lactic acid burn that causes like discomfort or forces you to stop. Like when you kind of are training that like lactate, quote unquote, lactate threshold, you're sort of training at that point, right? Like where you're starting to feel that burn in the muscles and you feel that accumulation of lactic acid. And while there is some association between an increase in acidity in the blood, it's not necessarily lactic acid. So you said lactate and lactic acid are 2 different things. They're often used interchangeably, and that's not necessarily like a huge deal, but essentially lactic acid is a state associated with the accumulation of lactate molecules in the blood, right? So when you start exercising and you're exercising at a relatively low to a moderate intensity, lactate production in the body starts to increase, but generally not enough to the point where it starts to accumulate in the blood because it's still being able to be utilized as a fuel source by slow twitch muscle fibers. So once you increase that exercise past that threshold, it starts to accumulate in the blood. And once it starts to accumulate in the blood, we start to see an accumulation of other strong cations, which are essentially just like positively charged hydrogens. And that's what's going to decrease your pH in the blood or increase the acidity of the blood. And it's those hydrogen ions that when they start to accumulate in muscle tissue, they're actually competing with calcium, binding to myofilaments, which are responsible for or part of the cross bridge cycle, which is essentially a muscle contraction. So the accumulation of hydrogen actually makes it harder for calcium to initiate a muscle contraction. So it just becomes harder and harder to contract as forcefully once we start to see that accumulation of hydrogen in the muscle. And that's generally what's going to be associated with decreases in muscle velocity, force output, contraction speed, contractile economy, things like that. And again, that's associated with the hydrogen accumulation and the competition with calcium, as opposed to the accumulation of lactic acid. And again, that acidity is just a decrease in blood pH, which partially has to do with the increase in lactate, but it also has to do with the accumulation of other weak acid buffers, as well as an increase in partial pressure of CO2. Like it's not just lactate that's causing that.
Yeah, so to kind of give a summary of the idea of lactate versus lactic acid, some sort of general chemistry concepts is that the pH, right, like the acidity of the blood, you know, as Sergio mentioned, it can be a somewhat complicated calculation to figure out exactly what the pH is if you start to account for all the different physiological pieces. But essentially pH in sort of broad strokes is referring to the concentration of hydrogen atom or ions in a solution, right? So hydrogen ions are positively charged, and the more hydrogen ions you have floating around in a solution, the lower the pH, meaning the more acidic that it is. And so if we think about a typical acid, whatever composition, someone can think of something like hydrochloric acid, hydrofluoric acid, etc. And if you look at the actual molecules that are making these up, it's one, in the case of hydrochloric acid, it's one molecule of hydrogen and one molecule of chlorine. And those paired together would be called hydrochloric acid. And then when you dissolve it in a solution, the hydrogen ion dissociates from the chlorine, and that's kind of floating around, right? So you have these simple molecules that are hydrogen paired with something else that are very acidic, because when you put them in solution, they just lose their hydrogen ions, and those are just floating around, and you have a very low pH, right? So similarly, lactate with a hydrogen ion on it would be called lactic acid, right? And so the idea is that, okay, in the body, you're not typically going to have lactic acid. You're going to have lactate on its own because it loses its hydrogen ion. But then, I think you started to touch on this a little bit, but there is a little bit of confusion and potentially even controversy as to whether or not lactic acid is even the byproduct, this sort of like metabolic byproduct, right? That it seems like we may actually produce lactate on its own, not lactic acid, which then dissociates into a hydrogen ion and a lactate molecule. And in this paper, I believe that they say they're unsure on it, but I think you mentioned something before we started recording that there is actual more clear data that we do just in fact produce lactate as a metabolic byproduct, not lactic acid. Can you dig into that a little bit?
Yeah, so lactate is essentially the conjugate version of lactic acid, right? It's like the base form. And actually, so lactate is an end product or a byproduct of glycolysis, which is the conversion of glucose into substrate that can be then converted down or broken down further into ATP. But the terminal step of glycolysis is catalyzed by an LDH, which is lactate dehydrogenase. So what it's actually doing is it's actually removing the acid. And lactate is essentially quoted as La with a negative sign because it's a negatively charged molecule. So it's produced as essentially an anion or a negatively charged molecule from glycolysis.
Got it. And so it is that hydrogen ion that's being removed by LDH, the lactate dehydrogenase. What's actually happening to that? Is that just being spit out into the blood and then, causing this whatever contractile fatigue, or is something else happening with that?
Yeah. So, this is why there's an association between there's a 1-to-1 coupling of hydrogen ion to lactate ions pumped into the blood, and so essentially hydrogen ion just starts to accumulate in the blood and it starts to cause a bunch of problems, whereas lactate is actually being taken and consumed and utilized as a fuel source.
Got it. So essentially the production of lactate, which is not causing fatigue and is in fact utilized, as a signaling molecule, as a metabolic fuel, etc., is 1-to-1 with production of these hydrogen ions, which do in fact cause fatigue by competing with calcium ions for binding sites on muscle fibers. Is that accurate?
That's correct.
Okay, got it. And then there's also some additional potential sources of hydrogen ions from, various fatigue pathways as well. Where else do we get hydrogen ions from?
Well, so hydrogen ions dissociate during what's called ATP hydrolysis. So essentially the breakdown of adenosine triphosphate in that process produces and releases hydrogen ions. And then I'm blanking on there's one more pathway that causes that.
We're putting you on the spot. That's okay. Well, we can add it in the show notes. But so essentially, overall, right, as we're engaging in these various metabolic pathways, we're spitting off these end products, and the hydrogen ions themselves, sort of like you mentioned, right, that it's probably worth kind of explaining this again in a little bit of detail, that these hydrogen ions will compete with calcium ions and inside the muscle, and that calcium ions are necessary to actually initiate a muscle contraction, right? That when you contract your muscle, the mechanism by which that happens is dependent upon a calcium ion binding. And if instead there's a hydrogen ion that binds in that same spot, then that makes that muscle contraction essentially at that spot not happen, which then causes you to have to recruit other fibers to get the same work done. Is that a reasonable summary?
Yeah, it's the hydrogen competing with the calcium that causes that issue.
Cool. And then, in some other podcasts where we talked to Evan Picon from Training Think Tank, what we see in those situations, right, is that the altered recruitment pattern there actually potentially results in a bunch of potential for hypertrophy, right? Because by blocking certain muscle fibers from contracting, you're forced to rely on other ones, and that potentially helps create hypertrophy. But then, in a fatigue-based setting as well, that also results in compensation, right? Because you're not able to get the normal type of contraction that you would get, so you have to use some sort of compensatory pattern to complete the work. And we see that all the time in people doing CrossFit or running, and they start to lose it. Do you have an example of like what that sort of looks like?
Yeah. So so the stage 2 of the CrossFit Games was this past weekend. And even I think one of the announcers had made a comment to the lactic acid buildup during this event, but it was the sprint sled sprint. So it was a 100-yard sprint, 100-yard sled sprint, 100-yard sprint. And Fraser and Quant had were racing for first, and they had kind of overtaken Noah Olsen on the sled portion. And then as soon as they got off the sled, they both kind of look like, and one of the announcers said this, they both kind of look like Bambis or like baby deer. And it looked like they literally couldn't move. And that potentially is where we would start to see, because of the accumulation or the stress or energy demand, there was a significant accumulation of lactate and hydrogen in the blood, and that's what was starting to cause that muscle failure. But coming off of the sled, the relative force demand probably decreased a little bit, so they were able to kind of just push through that. But at first, coming off that sled, they had that kind of weird run that was definitely a kind of a compensatory pattern, and it just didn't look like they were running naturally.
Yeah, totally. So, if you feel like, okay, I can't use my normal muscles to do this and I have to do something weird instead, very plausible that the actual accumulation of hydrogen ions in your muscle is stopping you from doing that. So it can seem a little bit pedantic to be like, well, it's actually it's not lactic acid, it's lactate, right? Like, but there is a reason that actually matters, is that the lactate itself is not the thing that's potentially causing fatigue in people. It's the actual hydrogen ions. Although that said, we touched on this a little bit last time, where it does seem like there's some possibility that lactate does inhibit the ability of the mitochondria to actually oxidize fat, right? So there is maybe some mechanism by which lactate itself can result in a potentially fatiguing type of metabolic situation. What's the actual deal with that? I mean, I think you looked into that a little bit after we recorded, because it was a line or two in the previous paper that they didn't say much about it, and it was like, oh, why does this inhibit this mitochondrial complex or whatever? So what's actually going on with that?
For sure. So you in the last episode you had mentioned that lactate inhibits lipolysis, which is the breakdown of fats, and we had mentioned that inverse correlation between fat utilization and lactate production. And so essentially what happens is when lactate and pyruvate start to get produced in large quantities, they start getting shuttled into the mitochondrial reticulum for oxidative breakdown, or for conversion back into energy. And when that's happening, acetyl-CoA is being produced. Acetyl-CoA upregulates malonyl-CoA in the mitochondrial reticulum. And then essentially malonyl-CoA is what starts to inhibit free fatty acids from entering the mitochondrial reticulum, which means they can't be broken down. So essentially what lactate is doing is there's this door that opens up via this molecule called CPT1. CPT1 opens this door. It's like a doorman, right? And then in walks a free fatty acid into the mitochondrial reticulum and use that. But lactate is like, yo, I'm going to stop you right there. Lactate increases acetyl-CoA production, which increases malonyl-CoA production. And the malonyl-CoA is like, yo, stop right there. You're not getting inside there. So the free fatty acid basically can't get inside the mitochondria to be oxidized and utilized for energy.
Lactate calls the doorman. Buzzes down to the doorman. No more of that.
Yeah.
So yeah, that's kind of interesting. And, I don't necessarily have a great model for why that would be the case, because typically in a lot of metabolism, things like this, you have interesting feedback loops where, certain byproducts cause other things to not happen or things to happen. And it's actually a pretty, I don't know what the right word is. Let's say elegant mechanism in a lot of ways, where end products result in inhibition of previous stages of metabolism to result in like an optimal outcome. In this case, it seems to me like what might be happening is that with the sort of preponderance of lactate, which may actually be a better fuel than free fatty acids, is that maybe lactate is just sort of saying, hey, like, you want to use us first, because we're going to be a much better thing to oxidize than these free fatty acids, that we can potentially be oxidized more quickly than the free fatty acids. And by virtue of the fact that there is so much of us, you probably need quick energy. So like, let's just put a hold on the free fatty acids and start spending lactate instead. And I'm not sure if that's actually correct, but that would be my intuition. What do you think?
Yeah. So, and I think this boils down to how quickly you actually need energy. So free fatty acids are going to, in turn, during one cycle of cellular respiration, the conversion or breakdown of fatty acids can produce way more ATP than that same process with like a glucose molecule or a lactate molecule. So fats do produce more energy, but it's a much slower process, right? So when you exceed the energy demands through an increase in relative power output in whatever you're doing, you're just going to need that energy way faster. And lactate and glucose are going to be able to provide that. And that's why we see that pretty significant increase in lactate production with a pretty rapid increase in exercise intensity. And generally there's the two values. There's RA and RD, lactate rate of appearance and lactate rate of disappearance. Essentially, this is just lactate production and lactate consumption. And so we generally will start to see this decrease in free fatty acid utilization when RA, so lactate production, start to exceed lactate consumption, and then that's when it starts to coagulate and start to sit in the blood, and that's what causes that like blocking of free fatty acids. And then in turn, you use less free fatty acids, you stress your glycolytic system more, you end up producing more lactate, and that just kind of induces this fatigue spiral if you can't really come out of that.
Yeah, and that's an interesting thing that it does seem a little bit surprising to me that it seems like it would kick off this positive feedback loop that would just continue to generate more lactate and then sort of like you said, go further down this potential fatigue spiral. And in a lot of other ways, there's mechanisms that stop things like that from happening. So I'm surprised that there isn't some way to stop that from happening. But it seems like it may just be, if you're going to try to use that much energy that quickly, you kind of deserve it. And so this is what we're going to do. I don't know. Okay, so we sort of talked about the actual role of lactate in creating fatigue. And the other thing that comes up often is soreness, right? That, I did all this yesterday and there's so much lactic acid in my quads or my calves or whatever, and I'm super sore. And that it's not lactate's fault. It's just lactate. Don't blame lactate. Don't blame lactate for that. So, Sergio, what's the deal with soreness? I mean, are we even concerned with hydrogen ions for soreness? What's the situation?
Well, and I don't understand too much about soreness, but what I understand about soreness is essentially it's just inflammation in muscle tissue from microtrauma, right? So when you are doing contractions and you're doing high volume contractions and you're doing contractions under significant load, you're creating a significant amount of damage, like tissue damage. And essentially it's recovery from that tissue damage that essentially induces the muscle to grow. So we need to induce that damage to essentially grow muscle, right? But it's inflammation. It's not a result of lactic acid buildup, because lactate is essentially that lactic acid is essentially cleared within an hour of exercise, right? Like it doesn't necessarily sit in the body. It's continuously being utilized as a fuel in tons of different ways.
Yeah, totally. And to your point, right, that soreness is actually surprisingly poorly understood, but my model for it is that it's essentially, like you said, a certain amount of tissue damage, but it also requires sensitivity to that kind of damage. And so what you typically see for people is they'll get very sore doing exercises that they haven't done before or done recently, right? Because in those situations, the brain is sensitive to that damage and is going to actually process it as pain. Whereas if someone is acclimated to the type of movement that they're doing at the intensity that they're doing it, they typically won't get very sore, right? So we see that if someone, takes 3 weeks off of training and comes back and does a workout with a bunch of lunges or a bunch of GHD sit-ups, they're absolutely wrecked. But if that person has been doing those movements consistently, they're just not sensitive to it. Think of it like developing some sort of neurological callus, the same way that you would like on your fingers playing guitar, or I don't know, what do people get calloused? Actually, a good example is like combat sports. I have basically no experience with them. But if you have not, actually punched a heavy bag before and you do it, you're like, this is insane. My knuckles hurt so much. But then if you do it a few times, it's not that it's necessarily, it is probably damaging your tissue less because you develop an adaptation in, the bony structure of your knuckles. But a big part of it is just neurological desensitization to that pain signal. And so we see that with soreness, right? That if you do something that you haven't done before and you accumulate tissue damage, you will feel sore. If you are used to it, your brain learns that this is not a signal worth paying attention to, and it will disregard it. And similarly to what we were saying before, people will often also get very sore after doing like a competition or a particularly high intensity workout, because based upon their effort and their intensity, they're pushing through fatigue more, they're inhibiting more muscle fibers that they normally use, and likely recruiting a bunch of stuff that they don't typically recruit in their normal training. And that's why people become excessively sore after competitions, even if they've been doing, volume appropriate to the level of competition that they're about to participate in.
Interesting. So what would you suggest for somebody? Because I've been told after a really hard workout, do like 10 minutes on the bike and roll out, and you're going to reduce muscle soreness the next day, or push off DOMs. So do you think that necessarily applies to that scenario?
Yeah. So it's funny because I think that is actually probably a little bit true, but just not for the reasons that people think it is. right? That like people think that they're flushing, like a lot of stuff, that there's a thing that you should maybe do and it might actually work, but the reasons that people tell you for it are probably wrong, right? Like if you're getting ART or like body work done, you're not having adhesions ripped apart in your muscle. Like that's almost certainly not happening, but it doesn't mean that body work is ineffective, right? So similarly with soreness, if someone is doing some sort of like tissue work after it, they're not like flushing lactic acid from their tissue or whatever, but by virtue of doing that type of tissue work, you're probably, speeding up the desensitization process as far as whatever minor pain signals from certain tissue, right? That's a big part of it, is just like, okay, if you can reduce the threat response and change the proprioception in this area, that tissue will often feel better. And, it has nothing to do with like accumulation of acid. And similarly, I mean, you mentioned like flushing on the bike or whatever, right? It's like, okay, is that necessary to clear lactic acid? Not really. Are there potentially other reasons that it might be worthwhile to do some moderate intensity aerobic work after a difficult session? Like, yeah, there's all kinds of them, right? It's just probably not the reason that people say it is. I don't know. What do you think?
Yeah. So one, I do want to touch on, that's an interesting idea, and I kind of want to look a little bit more into that, because I've seen like when people do the Grastins, right, and they see that like I guess what looks like bruising or like the blood vessels popping or whatever is happening underneath the skin, I'll be like, yeah, that's the lactic acid that was like built up in there. And I'm like, all right, I don't know if that's exactly true. But that's interesting. So as far as like flushing goes, I think so when we think about that state of acidity in the blood, like that doesn't, again, like I said before, that doesn't necessarily have to do with like just lactate and hydrogen. Like that potentially also has to do with like partial pressure of CO2 in the blood and O2. And so when you exercise, there's a significant increase in PCO2, or just levels of CO2 in the body. And so that's why when we think about breathing.
And then Sergio, just to interrupt you real quick, like, so what do you basically mean by that, right? Partial pressure, like what are we actually talking about here?
Yeah. So that's a good question. I think partial pressure of oxygen or CO2, you're essentially just measuring the level of CO2 and oxygen relative to other, molecules. Like I think, it's measured in, I believe, I want to say torr. And I think, I don't know exactly, do you know what torr represents?
Oh, the various pressure units.
Yeah.
And if you asked me a while ago, I could have probably told you, but no, I don't know.
Yeah. So it's just essentially like a measurement relative to other molecules, right? So it's like, there's this much CO2 here and there's this much O2 here. That's actually, sorry.
Yeah. So, I mean, I was just going to say that a useful way to potentially think about it would be, say you have a certain amount of pressure in, a given vessel, right? Like you can use something like let's use a bike tire as an example. Maybe this isn't the best example, but we're just kind of coming up with this on the fly, right? And you filled that up with just like air from the atmosphere, and there's a certain amount of pressure in your bike tire. I think that mine is what is it? It's like 100. I'm supposed to pump it up to like 100 psi, right? 100 pounds per square inch. I know that one. I don't know torr though. And that the atmosphere, like that I'm pumping into it, is a certain amount of oxygen, a certain amount of nitrogen, and a certain amount of carbon dioxide, right? And that we have a total amount of pressure, and you can consider the amount of pressure from each of those sort of segments of the atmosphere, and that would be the partial pressure of that specific compound, right? So just like, okay, what's the partial pressure of oxygen? What's the partial pressure of nitrogen? What's the partial pressure of carbon dioxide? And that would need to add up to the total pressure in my bike tire of 100 psi or whatever. So I don't know if that's clarifying at all, but that's the idea of talking about like partial pressure of carbon dioxide in the blood, post-exercise.
Yeah, and in physiology, they like throw that around a lot. So that measurement is used for in a lot of different tests. It's really important to measure relativity. Like oftentimes you'll see like, okay, this molecule exists in this state relative to this partial pressure of oxygen, because like that definitely matters. But bringing it back to what we were talking about.
Yeah, so you were just talking about trying to sort of like flush post-workout.
Yeah, so so when we think about like blood pH, like that's not only affected by just lactate and hydrogen, like that oftentimes has quite a bit to do with PCO2, and when you exercise, you increase the amount of CO2 that's being consumed relative to the amount of oxygen. The amount of CO2 that's being removed relative to the amount of oxygen that's being consumed. And when you start to exercise, you're essentially potentially putting your body in a state of lower levels of oxygen relative to the amount of CO2, and that also is going to accumulate to fatigue. And so when you take a nice deep exhale, you're essentially removing oxygen as well as CO2. And the longer you're able to take an exhale for, the more CO2 you're essentially able to remove. And that could potentially assist in reducing just global fatigue, is how much oxygen you're able to take in relative to how much CO2 you're able to remove, right? And post-exercise, specifically post-intense exercise, there's going to be that increase in CO2. So you want to think about getting as much CO2 as you can out and as much oxygen as you can back in relative to each other. And you could potentially do that by hopping on a bike, continuing to increase blood flow to the specific area, and then really focusing on taking nice deep exhales and consuming as much oxygen as you can, right? So when we think about like controlling your breathing during a workout, it's really, really important to, again, that has a lot to do with maintaining just executive function and global control, but also like potentially pushing out fatigue because you're taking nice deep exhales and removing as much of that CO2 as possible, which again is going to help keep your blood levels at a closer to homeostasis, or like a pH of like a 7 or neutral, right? Because that's essentially where we are always trying to get back to.
Yeah, totally. And not to get too sidetracked away from lactate, but I do think there's additional benefit, not necessarily, for like soreness per se, but stiffness, which I think are different actual outcomes from some sort of like cool down type of protocol, right? That a lot of let's just say like negative feelings from damaged muscles are going to be sort of like regulated neurologically in a way that is intended to protect you as an organism, right? So if your brain thinks that something is bad or wrong with part of your body, it will make that part of your body hurt, and it will reduce your ability to access that part of your body. So if you go from doing something super, super difficult, an example for me is I play recreational soccer, and if I play a super hard game and then just get in my car and drive home and get out, sometimes I feel very bad trying to get out of my car, right? But if I spend a little bit of time doing like a little bit of movement post game, that tends to help a lot. And I think a lot of that is just the neurological aspect of my brain realizing like, okay, there may be some tissue damage. We may have some metabolic waste built up. There may be some things going on in the legs here, but we were able to just kind of like move around and it wasn't a problem. So we don't need to like engage our defenses and sort of lock this area down. So I think that a lot of the benefit of like a flushing type of protocol in terms of stiffness is going to come more from the neurological aspect of your brain not needing to engage defense mechanisms than like some specific, metabolism of a metabolic byproduct.
Yeah, and I think the major takeaway from that is like it's still good to like roll out flush post a training session if you can. Like I always encourage my athletes to go for like a 10 or 15 minute walk, hop on the rower, do like a nasal breathing effort, something like that. And so the takeaway is just that it's like that soreness is not like the buildup of lactic acid.
Yeah, for sure. All right, so let's return to our friend lactate. So we sort of talked about the potential role in fatigue of lactate and associated hydrogen ions. And in this paper on the lactate shuttle theory, there's a lot of discussion of different uses of lactate in the body, right? Different tissues that can metabolize lactate, different pathways that lactate can go down as far as, being turned into something useful. And I mean, it's really quite remarkable, all the different mechanisms by which the body will sort of preferentially pull in and utilize lactate for a lot of important tissue. So Sergio, can you give us just like a brief summary of some of these, important lactate shuttles?
Yeah, so I think one of the coolest, I wouldn't say necessarily new, but relatively newer popular understandings of lactate is that it's this is it's a connection between oxidative and glycolytic pathways. So it essentially is a metabolite that connects to different energy systems, right? And lactate is used in pretty much every single cell in the body. And that's what the lactate shuttle theory starts to get at, is that there's this thing called the ANLS, which is the astrocyte neuron lactate shuttle, which is essentially, it just states that neurons have the capacity, neurons prefer glucose as a fuel source, but they also have the capacity to oxidize lactate. And at rest, neurons are utilizing and communicating with astrocytes. The 12% of that energy is coming from net lactate consumption, right? And during exercise, we know that executive function, just like general thinking, primarily relies on cerebral lactate uptake, right? So there was a study done where they took a group of men, they had them exercise, they measured BDNF, which is brain-derived neurotrophic factor, which is the main molecule which stimulates neurogenesis in the brain. And BDNF was essentially downregulated in the absence of lactate. So a decrease in cerebral function was directly correlated to a decrease in cerebral lactate uptake. So in certain situations, lactate is actually the preferred fuel source in the brain. And when lactate isn't properly being able to be utilized in excess, we see a decrease in just overall brain function, right? And that could potentially be why, if you don't necessarily have a positive relationship with lactate utilization, you start to see this significant decrease in cognitive function when you're in the middle of like a really hard workout, right? Like you can't really feel your feet anymore. You don't really know what you're doing on your thrusters. You're like doing some weird movement pattern because you can't really control your effort. That could potentially be associated to a decrease in cerebral lactate uptake. Lactate is also exchanged between like the liver and the kidneys. Cytosol mitochondria is intracellular lactate utilization. That's that production of lactate from glycolysis. That cytosolic production of lactate is then oxidized and uptaken by the mitochondria or reticulum and converted to energy. We also know that working skeletal tissue and myocardium or heart tissue utilizes lactate. There was an interesting study that measured pulmonary lactate utilization. So the utilization of lactate as an energy or a fuel source by the lungs. And the way they were able to see that was arterial blood flow. So blood going into the lungs had higher levels of lactate than blood coming out of the lungs. Sorry, I think I have that backwards. It was venous blood flow was higher in lactate than arterial blood flow.
But that would be right.
Yes.
The arteries would be supplying lactate to the lungs, which would then be metabolizing it, and it would be being shipped out. Yeah.
So the heart, essentially the amount of lactate coming into the lungs was about 70% higher than the amount of lactate coming out of the lungs, which means that lactate was being utilized as a fuel source by the lungs. We know in like clinical settings, lactate infusion is used for in patients that are experiencing heart failure. So lactate in performance settings and clinical settings has a lot of really positive functions.
Yeah, and it seems like it's actually preferentially utilized by a lot of these tissues, sort of like you're saying. And something that I think is really interesting is that little mention of that executive function being related to lactate metabolism, right? So the idea there is that can you explain what they did in that study again? I feel like I don't fully understand. Like how are they measuring executive function? Like what were they actually looking at?
Yeah, so if I'm being honest, I'm not entirely sure. I know the way they did the study was they put arterial and jugular bulb catheters in place. It was like a fairly invasive study.
Sounds very bad.
Yeah,
having anything inserted into your arteries is not good.
Quite literally during exercise.
Yeah, you don't want that.
No, and I even the way they described it in the paper was like, it was almost like surprisingly like 40 men like participated in this study. But we're obviously very thankful for that study. But what they basically did was they looked at the correlation between BDNF secretion, which is that brain-derived neurotrophic factor, and lactate utilization. And as lactate utilization decreased, BDNF expression decreased as well. And there is a potential correlation between that and decreases in just overall executive function.
Yeah, so something that could be interesting, sort of like you started to mention, would be, what is the role of executive function in terms of being able to maintain a pace that's difficult, to, have a solid pacing strategy, to maintain good technique, et cetera, right? That a lot of that does require executive function during a difficult workout. So there may be something else that's, the ability to kind of like regulate your pacing and push through something difficult may be dependent upon your brain's ability to sort of take up lactate and metabolize it effectively. So that may be a reason why some people, seemingly are able to just kind of like suffer better than others, because they retain much higher levels of executive function during exercise. I'd be curious to see more about that.
Yeah, that's really interesting. And I think at the end of the day, wherever you're utilizing lactate in whatever form in whatever cell, what we will often see is that like people come into like hospitals or ERs with sepsis and their lactic acid levels are really, really high, right? And so oftentimes I think that's why we see this association between lactic acid and like really bad things happening. And oftentimes it's just the fact that your body isn't really able to utilize or process that fuel properly, which is why it's not being uptaken by certain cells. Like for example, in training, right? Like when the glycolytic production of lactic acid exceeds the consumption from oxidative or slow twitch muscle fibers, it starts to accumulate in the blood. Right. And so it's just this like poor ability to utilize this fuel source that's causing it to accumulate in the blood. And so it really just is a biomarker for things that are going wrong. And it's not actually the thing that's causing those bad things to happen in the body, if that makes sense.
Yeah, totally. And to that point, actually, we didn't really talk too much about lactate's potential roles in signaling, right? And to that point, it's like, okay, if you're accumulating lactate, it's potentially indicative of other stuff that's going on, which may actually kick off some of the adaptations to training that we want, right? By virtue of lactate accumulating, that can indicate to the body like, hey, listen, like, we're doing something that's requiring a lot of energy. We should build better energy infrastructure around here so that we're fitter next time this happens. So what are some of the signaling roles that lactate has?
Well, we know one of the big ones that we know, and this is really big in neuroscience, is that lactate stimulates that BDNF production. And you start to create a more positive relationship between lactate BDNF expression, which again is directly correlated to it's directly correlated to improving brain function, brain growth, neurogenesis. When you have higher levels of BDNF expression, you're essentially reducing the potential to develop something like Alzheimer's, right? So BDNF is really important. And lactate utilization secretion increases BDNF. And that's why we see that potential benefit in neurogenesis from exercise, directly correlated to lactate and then BDNF expression.
Yeah, totally. It also seems to signal for increased mitochondrial density, right? That the production of lactate seems crucial as far as signaling the body to make more mitochondria, which is something that we want from our exercise, right? So by producing lactate, we're sending the signal like, hey, listen, we should have more of these little energy machines inside of our cells. So again, we're reliant upon lactate to actually get us the stuff that we want out of training. And it's not, this evil molecule designed to hurt us.
For sure. And I think it's also important to understand like how you are able to develop that positive relationship with lactate, right? So like lactate signals for the secretion of certain molecules that increase mitochondrial biogenesis, right? And then with an increase in mitochondrial biogenesis, you're able to utilize all substrate better, whether it's glucose, fatty acids, or lactate, right? So it's kind of like this cycle where it's like lactate stimulates mitochondrial biogenesis increases your affinity for lactate utilization. And so it's just this like very positive cycle where when you train, you induce just a positive relationship between the mitochondria lactate, and that just continues to grow the body.
Yeah. So in terms of practical takeaways, I mean, we talked through some ideas about thinking about recovery, the role of lactate and soreness, et cetera. With a lot of this stuff, again, it can be a little bit difficult to come up with a super clear practical prescription from it, and we're kind of okay with that. There is some really good stuff in here for folks who potentially have suffered from traumatic brain injury and all that, but I think that the audience for this podcast is more in thinking, okay, what can I actually do for myself or for athletes who I coach related to understanding lactate better? So Sergio, do we have anything that we think is like, a super actionable takeaway from this review paper?
Well, if I'm being honest, it's more of an explanation. There's a really good study that's titled, it's 1,026 studies on acute, I think it's on acute brain injury. And the first line basically just states that like we do all of these studies that, essentially it states that neuroprotection research is found to be really effective in every mammal but humans. So like we have all of this research, like we essentially are able to see what's happening in the quadricep of like a dog in regards to like lactate and mitochondrial biogenesis, but like how does this apply to people, right? So I think primarily in performance, we just know that improving your relationship with lactate overall is going to improve your ability to express varying power outputs and train at varying intensities. I think if you are obviously able to utilize better, your brain function is going to be better. You're going to be able to continue to exercise longer. But for the most part, I think it's really just an explanation of essentially what's happening in the body in regards to this molecule, and addressing a lot of the misconceptions that are associated with this molecule.
Yeah, totally. And I'll go ahead and just be wildly speculative and sort of talk well outside of the bounds of things that are actually shown in any of this research. But, one could make a pretty reasonable hypothesis that something that separates people who are elite in any sort of conditioning based sport, probably one of those key variables is going to be their ability to continuously metabolize lactate, right? That the folks who are able to kind of like generate a whole lot of energy, and then as such spit off a bunch of lactate and then utilize that lactate to then create more energy are going to be at an advantage in anything like cycling, like our last study that we talked about, CrossFit, running, etc. And so if we think about that as sort of like a lens through which we might want to consider training, we might be able to come up with some ideas, especially in mixed training, about, thinking through, can we increase this person's capacity to metabolize lactate in a way that doesn't just result in them completely bonking, right? Because that's something that we run into a lot with people who are, let's say, pretty good at something like CrossFit, is that it's really easy for them to just completely blow up on workouts. Whereas like you actually mentioned, utilizing the games as an example, you can see extremely high level athletes start to lose it in a workout, but they never actually completely bonk. Whereas someone who's nowhere near that good, you'll watch them just completely melt down on stuff all the time, right? Where it's like, oh, you did one too many handstand push-ups. Oh, you rode just like a little bit too fast on that. Like you are cooked for the rest of this workout. So I think that's something that's worth thinking about is, in training, can we potentially have someone sort of like modulate their effort up and down throughout a training session such that they're actually generating a bunch of lactate through, their training, but then not actually pushing so hard that they've completely fallen apart, and they're continuing to metabolize that lactate throughout the rest of their training session. That's probably something that's worth working on. And I think that a lot of intelligently designed interval training protocols will actually touch on a lot of that stuff. stuff, maybe not explicitly trying to do it, but that ends up being a big part of what's probably going on in those training sessions. Again, fully speculative, very hand wavy, but that's how I like to think about it, at least.
No, and that makes a lot of sense, right? Like when we think about this sport, in a sport like cycling, like it's really, really, I don't want to say really, really, it's fairly easy to measure or look at what you have to measure to gauge improvements in performance, right? Like you kind of can actually look at what substrate is being utilized primarily at what points of exercise. You can find like their for let's say like Tour de France cyclists, you can find like their fat max zone or like their zone 2 and like have them train at like this specific percentage at this exact wattage relative to their their heart rate for that day. It's like really easy to track that. Whereas like in this sport, there's a lot of things that could potentially contribute to poor performance. So as far as like training, I guess you could consider something like that, like energy system training, right? I think it's good to have just like, so as a coach, you start to develop these like general heuristics as to how often you dose certain styles of training. And it's not like in the middle of a workout, you can think like, okay, like I feel the lactate and hydrogen accumulating. I'm going to like stop that shit. You know what I mean? It's like, it's this consistency in your training at various intensities that's going to improve your affinity or your ability to utilize that lactate, right? And so like you said, certain protocols that if you do regularly, you will improve your body's ability to respond really positively when we start to see that increase in acidosis, right? And I think it's a good combination of high intensity interval training, which we know increases mitochondrial biogenesis, as well as something like zone 2, that like lower sustained cardio that we see done fairly often. It just, that improves your slow twitch muscle fibers' ability to utilize lactate, so that when your fast twitch muscle fibers start to kick in and you start to go really fast, that lactate is not just thrown into the blood, which starts that or causes that hydrogen accumulation. The slow twitch muscle fiber is able to kick in and be like, hey, I'm going to use you right now because I have a positive relationship with you, but the lactate. And in turn, that'll just continue to allow you to exercise, produce high power outputs, recover, stuff like that.
Yeah, totally. And to kind of maybe make what I was saying a little bit more tangible for folks, the sort of like old school, energy systems training model that a lot of folks are utilizing has a lot of like lactate stuff that's very, very high effort for a certain, let's say 30 seconds to 3 minutes with long rest periods. And you're absolutely going to be producing a lot of lactate when you do that. And it's pretty miserable. But I actually think that, utilizing some of these lactate shuttle models for what we actually want as a training adaptation, that we probably don't actually want that is not going to be terribly useful for a lot of CrossFit athletes because there's very few events that require them to actually go, at that level of effort at a totally unsustainable pace for a time frame like that. Instead, you have things that require them going pretty deep for a little bit of time and then switching to another movement and hopefully recovering while they do that other movement, right? And if we think about what may be happening with lactate throughout that process, you're potentially spitting off a bunch of lactate when you're doing a set of 15 chest to bar pull-ups, and then you have to, run around the block. And ideally, we can create training sessions for people that allow them to do something like chest to bar pull-ups or touch and go power snatches or whatever that's difficult for them, but then they move into something that allows them to then metabolize the lactate that they've spit out from that more challenging movement while doing something that sort of like allows them to recover while continuing to move, right? So I think that, if you look at the training of a lot of high level athletes, they're not really doing a lot of like power work or like that lactate repeat type of stuff, but they do a hell of a lot of EMOMs, right? With like kind of like varying degrees of difficulty. And you're just like, oh, that kind of makes sense that what you're probably actually doing there is really training this repeatability and this ability to metabolize lactate as a fuel source during a training session through that kind of like EMOM structure, or doing something where it's like every 2 minutes do this hard thing and then, ride the assault bike at a moderate pace for the rest of it. That's the type of thing that I think is potentially applicable, and this type of thinking about lactate might give a reason why that works.
100%. And I actually think on the last episode, you started to touch on this in that like higher level athletes actually produce way more lactate than like a normal individual potentially could. It's just their ability to utilize that, right? So it's not like these athletes are producing less lactate and that causes less problems, right? That causes less acidity in the blood, which then in turn affects their performance. But it's like you for example, if we look at the games, that event 1 started with the 1500 meter row, right? Like you want to be able to be working at an intensity where you are potentially starting to increase lactate coagulation in the blood, but you're not overdoing it to the point where you're starting to like experience that over acidity, which is associated with that muscle fatigue. And then but you're able to go hard enough where you're able to accumulate that lactate. And then as soon as you get off the rower, your body's able to the slow twitch muscle fiber is able to kick in, and other cells are able to take that extra lactate and convert it back into energy in a different fuel source, right? So it's like, even if you are switching between various energy systems constantly, it's your ability to kind of like take that end product and then turn it back into energy instead of just letting it sit there and cause more problems.
Totally. All right. Science with Sergio, episode number 2. We'll wrap it there. If any of you listening have other topics that you would like us to cover, feel free to reach out. You guys can shoot me an email. A lot of you are on my email list and respond with ideas about the podcast. So if you have things that you think would be good for us to potentially review some of the actual scientific literature on, send it over. We'd be interested in doing that. Thanks for listening. Thanks for listening. While you're here, go ahead and head over to your podcast player, subscribe to the show, give it a rating, give it a review, all that good stuff. You can also go ahead and click through to the show notes where you can find out more about us at legionsc.com and also follow us on Instagram at legion.sc.